Welcome back. So we're going to talk through the last couple sections of Chapter 7 here, um, just to kind of summarize things on ratio, proportion, and percentage. And so to start off, we just want to talk about ratio. And the idea of a ratio is very similar to that of a fraction. So a ratio is an ordered pair of numbers. Um, but there are two main distinctions. One is the way that we write them. We write a ratio A colon B instead of A over B, and we still want B to be non-zero. So we write a ratio differently than a fraction. But another way in which ratios are different than fractions is that ratios give us a little bit more option how to compare quantities. So when we talk about fractions, we talk about specifically this fraction talks about part to whole relationship. But in ratios, we can also explore the idea of thinking about a part to part relationship or even a whole to part relationship, which wasn't really, we didn't have a means for dealing with just a fraction. So again, it allows us to compare relative sizes of quantities, but not just part to whole. And so, for example, let's say we have a class of students, and we know that the ratio of girls to boys in the class is 8 to 6. So we'll say in this example, we're going to talk about two different ratios and talk about them explicitly. So in class 1, we have a ratio of girls to boys is 8 to 6. So that tells me that there's 8 girls for every 6 boys. In class 2, we have a ratio of girls to boys is 4 to 3. So there are 4 girls for every 3 boys. Let's suppose that in both of these classes, there are 28 students. So if I write out, or if I try to kind of somehow denote each student, so let me actually change these colors real quick so that this is clear. So let's do, when I'm talking about class B, let's say it's in pink and then in purple, or sorry, class 1 will be in pink and then class 2 will be in purple here. So for class 1, I have 28 students and the ratio of girls to boys is 8 to 6. So you can see here I have 4 groups of 4 girls, so that's 16 girls and 4 groups of 3 boys, that's 12 boys. Altogether, I should have 28 students in this little model. And so the ratio that this is depicting is kind of thinking of splitting this class into 2. There's 8 girls for every 6 boys. So this is what my ratio is representing in class 1. In class 2, what I'm representing is 4 girls for every 3 boys. Since we have the same number of students, and we can see this breaks up the class the same, these proportions represent the same exact classroom, right? So this tells me that these are equivalent ratios and they're the same relative amount. So what's different about the ratios is that we're talking about the ratio of girls to boys, which is not a part to whole relationship, unlike the fractions, where I might talk about the fraction might be relating girls to number of students in total. So in that case, the fraction relationship between girls in the whole class would be 16 to 28, or or between boys and the entire class would be 12 to 28. Okay, so this is kind of one of the main differences between ratios and fractions. We say that two ratios are equal or they represent the same proportion, basically if their fraction representation is equal. So a proportion is a statement that says two ratios are equal. So for instance, an example of two equal ratios would be the ratio of 10 to 12 and the ratio of 5 to 6. Okay, so those fractions are equal, so the ratio, the proportions of 10 to 12 is the same proportion as 5 to 6. Okay. Ratios involving different units are called rates. So here in our previous example, we were talking still about the same type of unit in a sense. We were just talking about students to student ratio, some of them being girls and some of them being boys. But if I'm talking about completely different units, I call these things rates. So maybe very common examples of rates would be miles per hour, um, actually, any sort of speed is a very common type of rate to encounter. So here's an example of a case where a question where we might have used rates to solve this problem. So a school orders 3 cartons of milk, and for every 7 students. There are 581 students in the school, and we want to know how many cartons of milk should be ordered. So I'm going to solve this using proportions. So I have 3 cartons of milk for every 7 students. And I want this proportion to be the same if I have 581 students. So the question is asking me, how many cartons do I want? So here, notice this is a rate because I'm talking about 2 different types of units, cartons and students. Okay, so to solve this, there are a few different options. I think your book mentions cross-multiplying. I think I've mentioned before how I'm not a huge fan of this term. It's because there's nothing implying that we need inequality to do that. Of course, we can cross-multiply though. I can multiply both sides by 7 and both sides by 581. Instead, what I would think of doing here is, let's see, I'll get rid of these units just for clarity. What I would think of doing here is using the idea of inverses. So I'm dividing on the right-hand side by 581, and I want to solve for n. The inverse operation to division is multiplication, so I'm going to multiply by 581 on both sides, which is really just 581 over 1. So I'm going to multiply 581 times 3 over 7. And I know on the right-hand side, I have 581 divided by 581. That's just 1. This is where inverses are really handy. And simplifying this fraction, this 581 times 3 over 7 all together, and I get 249. And since n represented the number of cartons of milk, it's 249 cartons that we would need. Okay, so this is what we call like using proportions to solve this problem. We're going to go into this in a little bit more detail when we talk about in the next section here. Section 7.4 is all about percents. Again, hopefully you're familiar with the notation. So the word percent comes from the Latin word per hundred. So in this example here, when I talk about when I have 32%, I'm saying that I have 32 over 100. So there are different, in a decimal form, I can write this as 0.32 because I have 32 hundredths, or I can write this as a fraction as 32 over 100. I could likewise simplify that fraction as 8 over 25, or reduce that fraction, or whatever phrase you like to use there. So those are equivalent ways of writing the same value, I guess, or proportion. So if I were doing the opposite and writing 1/16 as a decimal, well, I'd want to turn this into something involving hundreds. So because I'd like so I'm starting with a fraction and I want to not turn it into a decimal, but into a percentage. And again, just like I would with a decimal, I'd want to turn the denominator in terms of hundreds, right? So this is the same thing as 1 over 2 to the fourth. So I'm going to use the same trick where I multiply by powers of 5 on the top and the bottom in order to get powers of 10, okay? So I'm going to multiply 1 over 2 to the fourth by, well, I want the denominator to be 10 to the fourth, so I'm going to multiply by 5 to the fourth over 5 to the fourth. So this gives me 5 to the fourth over 10 to the fourth, or 625 over 10,000. And writing this as a decimal, this is 0.0625. If I write this in terms of hundreds, it's 6.25 over 100, or 6.25%. So this is just different ways I can represent this fraction or decimal. Right? But if I was trying to write it as a decimal, it would be 6.25%. And if I was trying to write it as a percentage, it would be 6.25%. And the most helpful way to do that is by trying to write it as a decimal first. Okay, looking at this mathematical task, 7.4b, here's a question to think about. So we have a wholesale price of a jacket and it's marked up 40% to obtain the retail price. So the buyer will buy it at the wholesale price and then sell it at this retail price, which is marked up 40% from the wholesale price. The retail price is marked down 40% to a sale price. Are the wholesale price and the sale price the same? If not, explain why not and determine which is larger. So I want you to think about this question a little bit. Maybe you have to read it a couple times. It's a mouthful to say out loud. I will give you a hint for this one. These two prices should not be the same. So the wholesale price and the sale price are actually not the same. So if you can see by these two little diagrams of these little tags, this is very misleading. It seems like if I added 40% on both sides to the sale price, I should get that the sale price and the wholesale price are exactly the same. But the piece in question here is that we're ignoring is really what we're taking the percentage of each time we add it or subtract it. So that's my hint for this task. So I encourage you to try to solve this one and try to figure out how you would explain it. This, I think, would be a good task if you want to present this in an office hour for participation. It will also help you with the one at the end of this section if you would like to present that one and talk to me about it. But of course, feel free to ask me about it in office hours or at some other time. Okay, continuing on, I want to finish off this section by examining 3 different examples that we can use 3 different approaches to solve. And so I should note that your book goes through this example in detail with these 3 different approaches on page 287. Let's put that here. It is example 7.31, 7.2 and 3.2 and 7.33, I think. Great. I don't know why my eraser is being weird. There we go. Okay. So if you want to read out the detail of how they've written up those problems, you can see that there. I'm just going to do a brief overview. So here are the 3 problems. The first one is a car was purchased for $13,000 with a 20% down payment. We want to know how much was that down payment. The second problem is we have 162 seniors and we know that's 90% of the senior class. And so we want to know that are going on a class trip. And so we want to know how many seniors in total there are. And the third problem, part C, says we have a student that scored 48 out of 60 points on a test, and we want to know what percentage she got correct. So the point of having these three different problems is they're getting at three different aspects of the proportion. And so that's what each of the problems represents. We're also going to talk about three different ways to solve them. So we're going to talk about a grid approach, a proportion approach, and an equation approach. So let's start with just looking at the grid approach for all three of these problems. And then we'll briefly talk about the other two approaches as well. So each one of these diagrams represents a different part of the problem. So this first diagram represents the problem A. Oops, there we go. The second one represents the problem B, and the third one represents the problem C. So let's just look at this first problem real quick. So again, a car was purchased in total for $13,000, and we put down a 20% down payment. We want to know how much money that actually is. So in the grid approach, the idea is that we want to have a visualization of this proportion or percentage that we have. And so for this first problem, what the grid represents is the entire $13,000. So this whole grid represents $13,000. And what we want to know is what 20% of that $13,000 is. And so notice we can count the boxes, but it's still just a 10 by 10 grid, so it consists of 100 squares. And so what that means is that each of these squares should represent 13,000 divided by 100. So each square should be $130, right? And if it's a 10 by 10 grid, then 20% of it is going to be 20 of these little boxes, right? Or 2 whole columns. And so in order to find out what the down payment is, we can just take each one of these little $130 boxes and multiply it by 20. And that should give me my down payment is $2,600. Great. So basically, I'm just summing up 20 of these boxes that represent $130. Okay, so what's nice about this grid approach is that it gives me a visual representation of kind of like what part each percentage is talking about. So we can contrast this example with example B. And in example B, we're talking about 162 seniors, but in this case, that's not all of the seniors. So that's not going to represent my entire grid. It's only 90% of the senior class. And so if this time the entire grid is all of the seniors, oops, got a little wiggly. Apparently I've had too much coffee this morning. Okay, so this is all seniors. Goodness. And so 162 seniors we know is 90% of that. So that's why this 162 represents these first 9 columns. And again, we can do a little bit of arithmetic to figure out what each box represents. And in order to do that, this time we're taking the 162, and we know that is not divided up again over all 100 squares, but over just 90 of them. And so 162 divided by 90 gives me 1.8. So each little square here represents 1.8 students. Of course, that means nothing in real life. We're not chopping up the students, but that's what this grid represents. Okay, so then if I want to know how many students there are in total, I just take that 1.8, which represents one of those little boxes, and I multiply it by 100 because I have 100 boxes, which represent each of the total number of seniors. So 1.8 times 100 is just 180 seniors. Okay, so the real distinction between problems A and B are the numbers that we were given with to start represent different pieces of my grid. So in problem A, 13,000 represented the entire grid. In problem B, 162 represented only a portion of the grid, the shaded blue portion. Comparing this with problem C, we have a very different picture. So here, Susan scored 48 points out of 60 points on a test. We want to know what percentage did she get correct. So now if I'm looking at the grid, the entire grid should represent all 60 points. And we know that Susan only got 48 of those points. So what we have is now to get what one single box is it should be 60 divided by 100, and one single box should represent 0.6 points. So basically what we then want to do is we want to add up 0.6 a bunch of times, right? We want to know how many times do we have to add up 0.6 to get 48. And that should be my solution, right? So that's the percentage that she got correct. So let's call it a variable so it doesn't look as confusing. We'll call it X. And so what I want to do then is really take X, and that should be 48 divided by 0.6. And that should give me 80%. Okay. So notice here, what we're really asking is how much of what we're now asking is how much of this grid should we be coloring in to represent that 40%, and we know it's really the first 8 columns is what the 48 points represents. Okay, so I think this grid approach is nice because it really helps us understand that when we ask questions about percentages, we have to really pay attention to what relationship each of the values takes with regards to the percent. So the proportion approach, which is our next approach, does a similar thing. So again, your book goes through this in more detail, but here is a kind of a snippet of the answer to this question, these 3 questions with regard to the proportion approach. But I think it's also a good demonstration of how what we're looking for changes with regard to the percent. So as you can see in problem A, when we're talking about the $13,000, see, we know the total purchase price. So here we don't know the total purchase price. We know that represents corresponds to the 100%. And we know we want to find out what 20% corresponds to. And so that's our unknown X. And so here, using a proportion, what we're going to do is we're going to set up a proportion, which is an equation relating these 2 fractions that we want to solve. So here, this tells me X divided by the 13,000 should be equal to 20 divided by 100. And then we're left to solve for X, and we get the 26,000. same answer, which should be no surprise. Question B, we can see through this chart, is referring to a different part of the proportion. So here again, we know we're talking about 90% of 100%, but this time what switched is where the unknown is, and the unknown now corresponds to the total as opposed to the fractional part of the percentage. And so so you'll notice that in setting up my proportion changes. So it's not x over 162 is equal to 90 over 100. Instead, it's 162 over x is equal to 90 over 100. So notice the difference between how I set up my proportions based on what my unknown is referring to here. And then, of course, it means I'll solve slightly differently. And in solving this equation, I have a few different ways I can do this, but once I solve, I still get 180 seniors should be my solution. Finally, for the third example, C, again, if I set up my proportions, this is a helpful way to illustrate we're asking for a different thing here entirely. We're asking about the percent. So here's the first time my unknown is in that percent column. And we're asking what percent does 48 correspond to out of the total 60 points. And so you'll notice when I set up my proportion, x is over 100 because I'm asking about the percentage, and that corresponds to the 48 over 60. So solving that, again, I just get 80% like I did before, but using a slightly different explanation or approach. Okay, so of course they give us the same answer, which is great, using a slightly different approach. The last approach is an equation approach. It's very similar to my proportion approach. The thing to keep in mind here is basically, again, we're just paying attention to what is the unknown. So notice in this kind of translation of the problem, they give a nice little diagram here. We have, in this first part, we have p% of n is x. So we're assuming x is the unknown. Kind of no matter what way you say blank percent of blank is something, we're going to have that p over 100 is equal to n, or p over 100 times the thing we're taking the percentage of is equal to x. So notice what's really changing in these three different equations is kind of what our unknown is. And each one corresponds to a different problem A, B, and C in this kind of setup. And so you'll notice problem A corresponds to this first explanation of what's happening. We're taking some percent of a number we already have, and that should be our unknown. So I just take 20 over 100 and multiply by that quantity we already know, and that's what gives us 2,600. In the second example, what we start with is we actually don't know the whole thing that we're taking 90% of. So I'm going to say 90% times x is equal to the 162 and solve that way. And in the last case, we don't know the percent that we need to take of 60 to get 48. And so that's where my unknown is. We have basically, this is the same equation written, three different ways based on what my unknown is. So this is very similarly related to my proportion, but kind of skipping kind of a lot of interpretation, I guess, and just thinking about it more in terms of percents as opposed to ratios or fractions. Okay, great. So three different approaches to solving the problem with different value. Obviously, we're going to have to do a little bit of arithmetic regardless, and so using an equation approach is really nice in that we can just plug things in right away, but the grid approach might be a little bit more illuminating as to what we're actually doing and help us understand the problem better. So That being said, I think these approaches are really helpful to help us understand what's going on with both the mathematical task we just mentioned, 7.4b and 7.4c, that I'm going to talk about here as well. This one, we want to solve the following problem and try to think about kind of what maybe solving it in a helpful and illuminating way about what's going on here. So you receive a coupon from Al's Appliance Shack that says that you can take an additional 10% off of anything in the store if a $450 washing machine is on sale for 20% off. How much does it cost to use the coupon and include a 7% sales tax? So again, both this problem and the previous mathematical task are helping us try to understand kind of what we're taking, or sorry, the questions that are really rooted in trying to understand what we're taking the percentage of. And really that's kind of what these three approaches, the different A, B, and C problems try to illuminate, is that it really matters what you're taking the percentage of when you're trying to solve problems like this. Okay, well, moving on, in our next video, we'll be talking about Chapter 8, and I'll see you next time.